All right, well, we are going to start a video that we're going to be using in our pre-calculus course. The title of this video is Writing Polynomials in Standard and Factored Form. Before we actually get started with doing a whole lot of fun math, let's start with some definitions. A polynomial is said to be written in factored form when it is expressed as f of x equals a times a linear factor that has one of the roots, times another linear factor, another linear factor. There might be n linear factors. There might just be 2 or 3 linear factors. The R1, R2, R3, those are all the roots of the polynomial. A is called the leading coefficient, and the degree will be determined by the number of roots. So if we look at this example, f of x equals negative 4x times x plus 3 times x minus 2 times x minus 2, this has been written in standard form. The leading coefficient is going to be negative 4. There's my leading coefficient. If I wanted to find the roots, I'm going to take each of the linear factors, set it equal to 0, and solve. So I have x equals 0, x plus 3 equals 0, x minus 2 equals 0, or x minus 2 is equal to 0. I would solve each of these linear factors. We get x equals 0, x equals negative 3, x equals 2, and x equals 2 again. This polynomial has 1, 2, 3, 4 roots. Now, although it has 4 roots, there are only 3 distinct, or if you will, different roots. And x equals 2, since it shows up twice, is called a root of multiplicity 2. Root of multiplicity 2. Okay. So let's look at some other examples, or another definition. A polynomial f of x is said to be written in standard form when it is expressed in this order. A sub 0 times x to the n. The a sub 0 is our leading coefficient. Now don't worry so much about these subscripts, the a sub 0, a sub 1, a sub 2, a sub n. That's just to indicate that these might be different constants. Since we don't know how many there are, to list them A, B, C, D, E doesn't really make sense. So we generally do a sub 0, a sub 1, a sub 2. The degree is the n, degree n. A0 is that leading coefficient. And this last term, the a sub n, is the constant term. Okay. So if we were to look at this example at the bottom, I have f of x equals negative 4x to the 5th plus 3x squared minus 2x plus pi. We have a degree 5 polynomial. The leading coefficient is negative 4. And the constant term is pi. Now, depending on where you are in the course, the fact that you have a degree 5 polynomial tells you a little bit about the behavior of the function. So does the leading coefficient, and so does the constant term. What it does help you to know is that the constant term means that you're going to have a y-intercept at 0, pi. The degree, if you have an odd degree, the tails, so what the function does as we approach, x approaches negative infinity, and what the function does as x approaches positive infinity. Degree 5, that's an odd degree. The tails will be pointing in different directions. Since the leading coefficient is negative, the first tail will be pointing up, and the second tail will be pointing down. Now, what exactly happens in between the two tails? Well, that depends specifically on the roots. But we do know, based on the degree, the leading coefficient, and the constant term, that the function will have these 3 characteristics. That as x approaches negative infinity, the y values approach positive infinity. And as x approaches positive infinity, the y values will approach negative infinity, and we'll have a root over here at 0, pi. A common task is, given the roots of a polynomial, we actually want to come up with the equation for the original polynomial. And so to do that, you could, depending on how comfortable you are, you could try to go straight to factored form, which is my preference, and then go to standard form, or sometimes you might want to go to standard form first. I think it's typical that you're going to want to go to factored form. So what do we know? I want to write a polynomial of least degree which has roots at -1/2, +3, -3, and a double root at x equals 0. I have 5 roots, so that means I'm going to be looking at a degree 5 polynomial. So my polynomial, if I'm going to think about this in factored form, will be a some constant, x minus the first root, x minus the second root, x minus the third root, x minus the fourth root, x minus the fifth root. My roots are, we have a x minus, the first root is -1/2, x minus 3, x minus -3, x minus 0, x minus 0. I can clean that up a little bit if we want to. We can say, all right, x minus a -1/2, we're going to make this x plus 1/2. X minus 3 times x plus 3. X minus 0 is x. Another x minus 0 makes it x squared. And so this would be a way to write this polynomial in factored form. And it'll have all the roots that I needed. Now, because I've not been given any additional information, we can't actually make any assumptions about a. What that means is there are infinitely many polynomials that would actually fit the description above. As long as they're of the form x plus 1/2 times x minus 3 times x plus 3 times x squared times some constant in the front, this polynomial has all the roots that we needed. Check. That's in factored form. Now, to get the polynomial into standard form, what we're going to have to do is actually multiply all of this out, and that's going to take a little bit of work. So let's try to be clever about this. If my goal is to get to standard form, well, that's going to involve multiplying out these factors. So we have f of x equals a. That x plus 1/2, because of the fraction, I want to multiply that out last. X minus 3 times x plus 3. Well, if you're at Yes Prep, you probably know the box really well. Since we're in pre-calculus, I would hope everyone would see this as a difference of squares, a factored version of the difference of squares. And so x minus 3 times x plus 3 is the same thing as x squared minus 9. And then times x squared. What else could I do? I can multiply the x plus 1/2 and the x squared minus 9. And I'm going to do what Mrs. Blakely likes to do. I'm going to go over here and do a little bit of side work. The side work is going to be my multiplying with the box. We have x plus 1/2. We have x squared minus 9. X times x squared is x cubed. X times -9 is -9x. 1/2 times x squared, 1/2 times -9. We put that all together, and now we have x cubed plus 1/2 x squared minus 9x minus 9/2. All of that's being multiplied by x squared. Okay, let's keep going. We're going to distribute the x squared through. X cubed times x squared is x to the 5th. 1/2 x squared times x squared is 1/2 x to the 4th. -9x times x squared is -9x cubed. Negative 9/2 times x squared is negative 9/2 x squared. You could multiply through by the a to get ax to the 5th plus a over 2x to the 4th minus 9ax cubed minus 9/2 a x squared. That would be the standard form of this polynomial. This guy up here is the factored form. Normally in a problem, we would give you some way of determining what the proper value for a is, and we'll see that in a later problem. But for right now, don't worry much about the a, just worry about the fact that if we give you the roots, you're going to, for each of the roots, write a corresponding linear factor. That'll give it to you in factored form. If you want the polynomial in standard form, you would have to multiply all of those linear factors together to get the expanded version. All right. Now this is a better one that we'll be able to figure out what the value of a is. We are told in this problem that we have a degree 3 polynomial function that passes through the points shown in the data table below. The x values are in the top row, the y values or f of x values are in the bottom row. We have negative 3, 0, negative 2, 6, negative 1, 0, 0, negative 14, and 7, 0. In part A, we're asked to write the polynomial in factored form. Well, the factored form will be f of x equals some constant, x minus the first root, x minus the second root times x minus the third root. Well, let's look at this table of values. A root occurs whenever the function is equal to 0. So I have a root over here at negative 3, I have a root at negative 1, and I have a root at 7. So let's see, instead of x minus r1, I can say x minus negative 3, which is the same as x plus 3. X minus negative 1, that's the same as x plus 1. X minus 7 is the third one. That's great. I've got my roots. If I multiplied this out, this would give me a degree 3 polynomial. Because I've been given this added information, I know that the function passes through the points negative 2, 6 and 0, negative 14. I can use either of these points to figure out the a value. So let's see. I'm going to use the point negative 2, 6. You could use the point 0, negative 14. That's probably the smarter choice, but I want to go through this with the point negative 2, 6 so that you can see the work a little more clearly. We know that if x is equal to negative 2, then the y value is equal to 6. So that gets me the equation 6 equals a. X is negative 2. So I'm going to replace all the x's with negative 2. We get 6 equals a. Negative 2 plus 3 is positive 1. Negative 2 plus 1 is negative 1. Negative 2 minus 7 is negative 9. Multiply those together. A times 1 is a, times negative 1 becomes negative a, times negative 9 becomes 9a. If we divide both sides by 9, we're going to get that a equals 2/3. So our final answer will be that f of x equals 2/3 times x plus 3 times x plus 1 times x minus 7. That would be our original polynomial written in factored form. Excellent. In part B, we're asked to determine the value of the constant term and the leading coefficient if f of x were to be written in standard form. To do this, I'm going to have to multiply the polynomial out. Now, depending on how comfortable you are with this, you have some options. All that we're asking for are the constant term and the leading coefficient. Now, let's see. Let's do this the long way first. Let me scoot this up. we have f of x equals 2/3 x plus 3 times x plus